Last week we covered some very important topics. I encourage you to review your notes and also review the answers you wrote out to the weekly objectives listed on the Week 12 intro page. Last week we covered the following major topics: the continental drift hypothesis, plate tectonic theory, and the scientific advancements that led to that theory, the three types of plate boundaries and their subtypes, and notably plate boundaries and their subtypes is a very important topic. We also covered hotspots and volcanism. When we discussed volcanism, we covered the distribution of volcanoes around the world, why they're where they are. We covered landforms associated with volcanism, including, but not limited to, the 4 different types of volcanic peaks. And then finally, we also covered hazards associated with volcanism. Wow, that's a lot. Again, I encourage you to review last week's material. This week, we continue our discussion of Earth's internal processes and cover the following major topics: intrusive igneous structures, also called plutonic structures or landforms. We cover folds, 3 different types of folds, and we cover faults, 3 major types of faults and some subtypes. We cover joints, and then finally earthquakes. There are several video clips in this week's lesson. Be sure to watch them all in their entirety at least once, perhaps several times. Also, be sure to answer the learning objectives on the Week 13 intro page. I highly encourage you to write out answers to these questions and to any questions that I pose within the video clips. Alrighty, let's get started. Be sure to take notes. 2 weeks ago, we introduced igneous rocks, and we learned that there are both intrusive igneous rocks and extrusive igneous rocks. We learned that intrusive igneous rocks cool slowly deep within the Earth and have large crystals, and extrusive igneous rocks cool quickly at or near the Earth's surface, and thus have smaller crystals. In general, extrusive rocks are associated with volcanism, and intrusive rocks form deep in the Earth, perhaps beneath volcanoes, perhaps not, and these rocks and structures will only be exposed after a whole lot of erosion has removed all of the overlying material. So when we see extrusive igneous rocks, like basalt and other extrusive igneous rocks, as shown in this diagram, we know that volcanism was likely present, because these rocks form as magma comes right out of the Earth and cools quickly. When we see intrusive igneous rocks, like this picture here, and also what we see in the Sierras in California, we know those rocks actually cooled deep below the Earth very slowly over millions of years, and the only reason we can see them now is that erosion has taken away a whole lot of material. So think of the Sierras. All those rocks in the Sierras formed deep in the Earth, perhaps as magma chambers underneath former volcanoes. We only see them now because miles and miles of material has eroded away from the Earth's surface. Last week we studied extrusive igneous structures, volcanic landforms. You remember the term volcano or volcanic comes from Vulcan, the Roman god of fire. So these are features that form at the surface of the Earth from fire, or more accurately, from volcanism. We covered last week 4 different types of volcanic peaks. You should be able to list them and describe each of them, by the way. We also covered basalt plateaus and calderas. All of the structures we covered last week were volcanic or extrusive landforms. This week, we're going to look at the intrusive landforms, which are also called Plutonic landforms, or Plutons. They are named for the Roman god Pluto, the god of the underworld. And these are features, or landforms, that form deep in the Earth as magma cools slowly, and the only way we see them is when erosion has removed the overlying material. Pluton is a general term for any intrusive igneous body. Check out the diagram here, and you can see that the volcanic structures form on the Earth's surface as lava cools quickly, forming small crystals. And thus these volcanic structures, the volcanic peaks, the lava plateaus, etc., are made out of extrusive igneous rock, such as basalt, andesite, and rhyolite. The plutonic features form deep in the Earth as the magma cools slowly, forming large crystals. Thus, plutonic structures are generally made out of intrusive igneous rock, such as granite, diorite, and gabbro. Notice that the plutonic features are essentially the old magma chambers and other bits of underground magma that has worked itself into cracks and cooled. We will study 4 specific plutonic landforms, 4 specific plutons: batholiths, laccoliths, dikes, and sills. We classify plutonic features by 2 criteria: their shape and their orientation. The shape can be either massive, which I like to describe as a big old blob, or tabular, which is a planar feature, although on a diagram it can look more like a linear feature. Let's look first at a batholith. Batholiths are essentially old, cooled magma chambers. Would you say that it looks massive or tabular? Is it a big old blob, or is it a linear feature? Hopefully you said it's massive. In terms of orientation, is it concordant or discordant? And what we mean by that, concordant means that the feature lies between sedimentary layers. It doesn't cut across sedimentary layers. Whereas a discordant feature cuts across the other layers around it. You can think of these terms as agreeing and disagreeing. Concordant or agreement means that the feature lies in between sedimentary layers and essentially is a linear feature as well. A discordant or disagreeing feature cuts across all of the layers around it. So let's look at the batholith. Does it lie neatly in between the sedimentary layers around it? No, it cuts right on through them. So a batholith is massive and discordant. That's what makes it a batholith. Next, let's look at laccoliths. Laccoliths are essentially a little blister of magma that is intruded between sedimentary layers. You'll notice that it doesn't have a linear look to it. It is a big old blob, so it's massive. But in this case here, it is actually slipped in between the sedimentary layers. So it's concordant. Perhaps we can see that better on this slide here, where we see the magma has come up and it's just pushed up the sedimentary layers. And as that cools and crystallizes, it's going to create a laccolith, which again we will never see unless erosion removes over all the overlying material. Dikes and sills are both more tabular features. On this diagram they look linear, but you have to remember that this goes into 3 dimensions, so it'd be more like a planar feature. So dikes and sills both have that linear look to them here, so they're tabular. In terms of their orientation, the difference between a dike and a sill is that dikes are discordant. They cut across the sedimentary layers. It's basically magma that is just working its way up through a crack, and then it cools and crystallizes. And sills, you can just barely see them on this diagram here. Sills are in between sedimentary layers. The magma has found a crack in between sedimentary layers, and it's filling that in. Okay, so sills and dikes are both tabular, dikes are discordant, and sills are concordant. Pause the video and study this diagram until you feel confident that you understand both how volcanic landforms form and also plutonic landforms form. And be sure that you can identify dikes, sills, laccoliths, and batholiths in these diagrams. Your textbook has an animation on volcanic and plutonic landforms, which I'm going to show you here. This is also a reminder to always watch the video clips associated with your textbook. If you don't have an ebook, you'll need to go to Mastering Geography to watch the video clips. Let's check this one out here.
Igneous features. When magma cools and solidifies below the surface, it forms plutonic or intrusive igneous rock. When this rock is exposed at the surface, it is called an igneous intrusion. As the animation begins, magma is rising toward the surface. The magma chamber feeds several large volcanoes and a group of cinder cones on the surface through conduits, as well as a large fissure eruption on the surface. Notice that the magma is also moving into cracks and bedding planes beneath the surface. When the igneous activity ends, the magma cools into intrusive igneous features such as dikes, sills, and a laccolith. A period of erosion follows. You now see an exposed dike and a volcanic neck. The laccolith has now been exposed as a gently rounded dome of plutonic rock. Further erosion exposes a batholith on the surface. Batholiths form the core of many major mountain ranges, such as the Sierra Nevada in California.
You should be able to give real-world examples for the 4 different types of volcanic peaks and the other volcanic landforms we studied last week. For the plutonic structures, I'm only asking that you know a real-world example for a batholith. And specifically, you should know that the Sierra Nevada mountain range is a batholith. Indeed, the Sierras represent a series of old magma chambers for ancient volcanoes that have long ago eroded away. Pretty cool, eh? The relationship between batholiths, and indeed all plutons, and erosion is worth restating one more time. The only way we see plutonic structures on the surface of the Earth is if a whole lot of that overlying material, in some cases miles of overlying material, is taken away through erosion due to running water, wind, or glacial ice. So what does a batholith look like on the surface of the Earth? Well, think of the Sierras. The Sierra Nevada mountain range is a batholith, or mini batholiths, actually. What do these other features look like at the surface? Well, a dike, which we know is a tabular discordant feature formed deep beneath the Earth, can sometimes also be exposed at the Earth's surface if erosion takes away the overlying material. And what you have left looks like a wall of sorts. Looks like a man-made rock wall, but indeed it's not. It's an intrusive igneous feature. It's a plutonic feature called a dike. Sills can also be present. Here's a side of a cliff where a sill is shown. And you might think, well, how do you know that wasn't just a lava flow? How do we know it's a sill and not a lava flow? That's an interesting question. I encourage you to pause the video for a moment and try to figure out how you would differentiate between a sill and a lava flow. Did you come up with some ideas? Well, a lava flow would be made out of extrusive igneous rock, and a sill like this one here would be made out of intrusive igneous rock, so larger crystals. Also, a sill would likely have evidence of contact metamorphism, right? Heating of the rocks around it, both on the top and the bottom of the rock unit. So if this rocks here were limestone, we might expect a little bit of marble between this sill and the overlying and underlying material. Pause the video here and make sure that you can answer all 4 of these questions. I encourage you to take notes on these and answer them in writing. This will be a great study aid when you approach the exam in a few weeks. So pause the video and answer these questions.